to, again, our VWR staff, the experts on this, and let them have some discussion. And Dean, I think that you are up first, is that right?
You don't need that.
So I'm going to briefly be talking about today is the issue of efficiencies. And Scott's pulling it up here. So what I want to talk about for about 8-10 minutes today is just considerations on the efficiency variable when we're doing HCU analysis. And really this is targeted towards just to have some open discussion and dialogue about what efficiency means, how it's used in the literature, what we look for when we're looking at an HCU analysis. And what we notice is that there's a lot of confusion on efficiency. There's a lot of different references to efficiency out in the literature, and maybe how can we consider what literature is saying about efficiency and roll that into our models or HCU analysis. We're not advancing that.
Is it on the left side? Hang on. Now try. Hang on.
There we go. So I was just going to start with a quote that came out of a paper that John Andrews wrote a while back, and I think this was an issue that the NRCS was dealing with years ago. And he made this comment that the term efficiency has many varied definitions with respect to irrigation systems. And quite often the rule of thumb values are applied without consideration of the meaning or individual characteristics. Individual characteristics that affect efficiency from system to system and site to site. And so I think that's a similar issue that we have had at evalua and efficiencies. Thanks. So I want to provide just a couple definitions of efficiency that we look at. And in general, when we're saying efficiency, we're looking at the performance of an irrigation system expressed as a percent. And then we can have multiple definitions or takeoffs from that. We have application efficiency, and when we look at what the ASCE task committee on defining efficiency and uniformity says, that application efficiency is typically related to a single irrigation event, whereas irrigation efficiency is often referred to as the average of multiple irrigation events over a period of time. So, we're thinking about how to distinguish those. Also, potential or theoretical design efficiencies. We use this term quite often, and when we look at what literature says about that, they're really looking at the potential efficiency that can be obtained, assuming proper timing and proper management. And really that's the optimum application efficiency that may be used throughout the irrigation year. And typically that happens during the peak performance, the peak period use of the crop. So these are just some general terms that appear in literature, and we just want to throw those out and see how maybe those relate to what we see in literature when we're talking about the term efficiency. So I have a couple examples of the use of efficiency in literature. And the first one, they talk about application efficiencies of X% are common, and potential efficiencies with properly designed maintained managed systems can be something else. And so what I think this publication is really saying is that you may go out in the field and determine that certain application events achieve a certain efficiency, even though you can calculate or determine the potential efficiency could have been some other numbers. In the second example, efficiencies measured in the field, I think is in reference to application efficiency. Somebody went out and looked on that day, this was the efficiency that was measured. And they make the comment that that might be different than a theoretical design efficiency, again, that could be assumed as optimal. We also see reference to seasonal average efficiencies, which represents what the average application efficiency was for all the events during an irrigation season. And they contrast that in this publication to single events. The seasonal averages differ from what was achieved during single events. So I think it's important to consider these definitions in terms of looking at literature and maybe how these efficiency terms apply in terms of analysis. And the last one is again just distinguishing between single events and the seasonal average. One thing we've also noticed in looking at literature regarding efficiencies is that there's a lot of reference to efficiencies changing throughout an irrigation season, and they're not typically constant. And that season-long efficiencies might be lower in the early season or later in the year due to various reasons: water requirements, soil intake rates, plant growth. And so we have a couple of references to that. And what I've shown here is just a hypothetical graph of what literature has talked about as how efficiency, single event application efficiencies may change over an irrigation season to help show that the seasonal average might be different than single events. So how do we apply this in a model? How do we look at what literature says about efficiencies when we're looking at models? And if I take IDSU just as an example, it was designed for determining augmentation requirements for groundwater wells. And they really talk about efficiency, meaning the efficiency of irrigation. And that's how they really defined it. And so it's really talking about the performance of the system. And in IDSU, you can enter a single value, or you can enter monthly values. So in addition, those values that you enter really require an assumption. And I think most of us, when we're looking at what assumption do we use in the model, we go back to the literature and see, well, what does the literature say? So I think it's important to understand the terms of efficiency, how it's used in the model, and then the limitations in the model. Most of these models have been designed where it's intended to represent full irrigation. They take the amount of water that we are inputting in as a supply and evenly distributing it over the acreage. So how does that affect the efficiency assumption that we use in the model? And so what we've come up with is that when we look at what efficiency should we be using, and maybe come back to literature as far as the sources, we tend to think about, is the system water adequate or water long? And when we have a system that fits that category, that efficiency value that we are using in the model may represent an optimal value for a single event during the peak use. But when we're water short, that efficiency value may actually represent the actual efficiency since we're limited by the supply. And the same thing with the demand-based analysis where the HCU is often divided by the efficiency. What we're saying is that we know what the actual efficiency is, and that efficiency assumption represents the actual efficiency of the system, and maybe not the maximum as we might use it in other contexts. So again, I think when we think about these models and looking at literature and reference of efficiencies, we have to look at the context in which we're using it and the context in which the efficiency values have been reported. Here's just a hypothetical comparison of what I was trying to say. We have a water-long system model with an input of 65% as an efficiency value. And throughout the season, the efficiency changes based upon supply and demand. And we actually hit 65 in July, which was the optimal max, which seems reasonable, seems consistent. But overall, we get this long curve, and you can see on the blue line, we get this curve which shows what the efficiencies were throughout the season. And that generally represents what we've seen in literature as well, that efficiencies change throughout the season. But when we model a water short, or we look at a demand-based analysis where we input 65%, we typically get a flat line. And it's just something to consider again when we're looking at efficiencies and modeling efficiencies. and how they relate to what's been reported in literature. So questions that we ask ourselves when looking at these models and looking at efficiencies and analyses is the assumed efficiency input consistent with the facts and literature? So what number are we sticking in the model? Is that consistent with what we've seen? What context was the reference that we used in referring to efficiencies? Were they talking about potential efficiencies? Were they talking about seasonal averages? Were they talking about irrigation efficiencies? What context was the reference that we used to base our input on? And is that assumed efficiency consistent with the irrigation system? Are we giving considerations to what the literature says about that number? Was it well designed, well managed? So that's all on the input into the model. And then we also ask, is the model modeling water adequate, water long, and water short? And does this input that we're using in the model represent a maximum value, or are we saying that this input that we're using represents the actual value of efficiency of the irrigation system? And then what we look at typically is what was the output? And when we ran the model and got the output, is that output consistent with published data in literature? And for example, we might look at, does the irrigation efficiency vary throughout the season? Is it consistent with literature? Is it consistent with what else we've seen? So just a quick insight into efficiencies.
Yeah, thanks, Dean. We're going to wait for questions. You can just ask all the panelists questions again, so I'll ask Kelly to come up. And he's got some things to share on some development from
trying to shorten what I was talking on. I realize much more interesting and creative. I was going to get a little bit in the weeds on HCU analysis, and I'll shorten that a little bit, but touch on some things that Dean has done. But as much of a point of that is to relate to those complexities to what we're doing on our tools that we support at the state, and how we're doing some additional development and what we're planning on those. I guess the complex part of the HCU analysis, I was going to initially start with crop coefficients. We really have recommended in many cases, if you're going to use blading criddle, to calculate potential evapotranspiration, PET, we really have often suggested you need to come up with a localized calibrated crop coefficient. In many areas, we do have now these coagulant stations that have been in place for 5, 10, 15 years, and we have that data. So to develop those calibrated crop coefficients, you might use a more advanced method, the ASCE standardized minimum teeth, for example, to calculate ET for that coagulant station for a short period of time. And then at a nearby NOAA station that just has temperature back into time, you can do that comparison to come up with individual crop coefficients to try to match that time period where you have data for the coagulant. So you can apply that back in time. And that is a fairly extensive process. We acknowledge that. We have done some development as part of the DSS projects on crop coefficient calibration. Obviously, in the HI model in the Arkansas, we do that. But for instance, in the South Platte, those DSS coefficients were developed for 2 general areas. So I think we've really suggested that's probably too large of a calibration. That we would really suggest if you do have a coagulant station near you, that you would do your own localized calibration, and given the conditions that you have. But that is complex. As I was saying, Dean has really done a lot of work. I'm really talking on his suggestions here. But he did suggest a more simplified approach to using blading criddle, where you could use elevation corrections, but with the important point that we don't do elevation corrections as has been done, where you blanket correct everything from sea level. We're really adamant that is not the correct way to do that. But really, the original writers and researchers associated with blading criddle and TR21 have suggested that if you're going to do an elevation correction, it should be only from the location that those original TR21 coefficients were developed. So Dean has really done some great work, developed a forensic analysis and a memo that's tried to tried to sort out where those tier 21 coefficients were developed. And so you do have an idea that for each individual crop, you could correct that crop from the elevation that was corrected. But again, that is a fairly complicated process. The tool that we really support for HCU analysis, HCU, at the state, you can definitely do those calibrated crop coefficient work in HCU, but it takes a big effort. You can do this other process that Dean has laid out, but it's tough. And so we would really recommend you using that. But I know, at least for us in-house, that's a pretty significant process. So that's why we have been working on some other tools and thoughts. We have recently been working on the development of a tool we call the least fallow tool. And the purpose of the least fallow tool really had two parts, but it was to streamline, simplify, and standardize HCU analysis. And to simplify and streamline the review, in particular of least fallow projects, and definitely in particular these pilot projects that are spelled out as far as House Bill 13-1248, where we can do some least fallow pilot projects. But we did finish up that project. There's people in the crowd that were really involved with that project. We do have the final version posted online in 3 different websites. It's on our water resources site. If you go to the modeling and DSS sections, it's also on the CWCD website through the, I think, technical resources tab, and also the CDSS website. So you can get to that current tool that we've been working on to simplify and streamline things. And it definitely has a lot of power. Little Division 2 specific, Arkansas River specific for doing HCU analysis, but it is, as it is right now, geared towards these least fallow projects, pilot projects in particular. But I think many of us at the State Engineer's Office and at Media we have an interest, at least for our own analysis, in simplifying and streamlining HCU analysis. And so we have continued to develop on that least fallow tool. And so right now, we're working on a version 7 that does include Dean's proposed way to do elevation corrections. So you just put in the elevation for your parcel, and it's going to figure out crop by crop how to do those corrections. We're adding a lot of coagment data. We have some in there for Arkansas, but we're going to add a lot of coagment data that will be quality control checked. We really propose that we should follow the ASE guidelines on how to quality check all that coagment data. And we often, as far as the Arkansas work, we often correct the solar data pretty intensely, and it changes things. So we will have done that and have that data processed and have crop ETs and reference ETs in there so that we can do those calibrated crop coefficient calculations more easily in a simplified way. So we throw that out. The other thing to note about the least fallow tool is it was developed on the basis of ISAM, the Irrigation Systems Analysis Model that Bill Tyner here really deserves all the credit in developing. That pulled the consumptive use subroutine out of the HI model to develop a tool, and as such, the HI model does model some processes that are more conservative than what State CU would indicate as far as how it considers use of irrigation water versus precipitation water. And so as such, we really do feel like, in the lower Arkansas, from Pueblo Reservoir to the state line, we would really like to, change water case, have those processes, those more conservative processes acknowledged, or at least when we do a review of a case, we'd like to check and make sure we're not having a compact issue by not acknowledging those in the analysis. And so we may use elements of the least fallow tool in Division 2 in particular to look at those things to ensure that we're not looking at those processes. But in a bigger picture, I guess maybe the point of all this is that really, State CU is our tool that we use and recommend, and we say is the gold standard for HCU analysis, and that's what we can support. And so if there's nothing more from the least fallow tool that we have on a wider scale, at least we're going to clarify and learn a bunch of processes and features that we want to incorporate in the State CU. So we really do have a plan through the ArcDSS project through the open source project that the CWCB is currently putting out to add some options and features in the state CU that will both simplify and streamline things as well as acknowledgement processes that we do. So I guess that was my point. That at EWR, we really are looking to simplify and streamline HCU and standardize, at least for our own internal analysis, if nothing more, how we look at these things. Thank you.